you.
You were using the old program file. You didn't check your new file.
I should have done
anyway,
that. I've got it in front of me now. I'll make those changes. So anyway.
Yeah, go ahead and get started.
So what I'm going to do, I had some confusion getting the it all started. So what I might do is let me just go to find where I'm going to share my screen. Can you see the screen now, the one that says Sage Workshop?
Yeah.
Yeah, we can see your screen.
Great. So hard to know sometimes which screen I'm sharing, but this is the one I'm meant to be sharing. So welcome everybody. So I'm Alasdair McAndrew from Victoria University in Melbourne, Australia. Should you wish to contact me, that's my details. Now, I was hoping we were going to use CoCalc in a sort of a nice sort of collaborative way. That's not really possible. So what I'm going to do, I'm going to put some files in the chat and see if I can, actually, can I, let's have a look. Give me a moment while I just get myself sorted out here. I'm putting two files in the chat. Can you see those two files? What you need to do is to download them to your local computer, just so you have them yourself, and then follow the instructions you can see on the screen. So go to https://cocalc.com, create yourself a little an account. See if you can do the first one. If you can't, if it's too hard, I'll email the files to you. If you can send me your emails between now and tomorrow, and we'll work out some way of doing it. CoCalc is very nice because it enables you to use Sage and all the attendant tools without having to download anything. You can use it for free, but if you do so, you get a rather, it's a bit slow, but you can pay for a license, which are quite cheap, and then you get access to more of the machinery that runs it, greater speed, and, all the rest of it. So if you can do that, that would be wonderful. If you can't, it doesn't matter, and we'll just sort of go on because I can talk about this myself. But I might also ask while you're doing this, has anybody here used Sage before? I know, Ajit, you have. You were telling me yesterday you've even written some books about it, so you probably know rather more about it than I do, in fact.
No, not at all. I think you are much better equipped.
Oh, I don't know about that. Wei Ching, have you used Sage before?
Not really.
No, maybe he's...
No, not really.
Okay. So you should be able to access CoCalc. I don't think... whereabouts in the world are you? Are you in Prague at the moment, or...?
Yeah, okay.
Okay.
Yeah.
I know that in some parts of the world there are restrictions on what parts of the internet you can access, but I think CoCalc is I should not think there'd be any problem in accessing it wherever you are.
Oh, okay. Yeah.
So see if you can download it and get it going. If you can't, it doesn't really matter, because what we should see is something that looks like, in the end, sort of a
Okay.
a list of sort of cells, if you like, with Sage commands in them.
Okay, I see it now.
But even before we start, you should be aware that if you go to the base URL, sagemath.org, there's a vast amount of information. It's a really, very, very well documented program. And if you go to the help documentation, you'll find there's, in English, happily for me, there's a tour and there's constructions on all different sorts of things like group theory, number theory, calculus, graphics, anything you like, and also in all these different languages. And if there's a language missing, well, you can always write one yourself. They're always looking for translators. But there's a sense in which this workshop is almost unnecessary because there's so much good information on the Sage website. You just go to, say, constructions alone, and well, you can see all the different things on the left-hand side. Some of which are quite complicated, modular forms. I don't know much about those. That's fairly high-tech mathematics, but Sage does do high-tech mathematics, elliptic curves, all that sort of stuff. So well worth having a play around just on the Sage Math website itself, just to get an indication of how Sage works and the way it does things. The other thing I should say is that Sage is based all around the programming language Python, which in itself is a very good thing because in using Sage, you get better at using Python, which, as you know, is a worldwide, very powerful language used in all sorts of different places. And I believe it's actually possible to use Sage as a Python library. I haven't done it myself, but apparently you can do it. But the nice thing about Sage is because it's based around Python, you've got all the power of Python. You've got all the Python libraries are part of Sage. So if Sage can't do something natively, then there's probably a Python library which can do it for you. So let me have a look at this. Now, is this big enough to see what I'm doing at the moment? Can you see that okay? Should I make these any bigger?
I think it will slightly bigger would be better.
Okay, let's have a look. I think, how's that? Is that good or more?
Yes, little more. Yeah, that's fine.
Tell me when. Is that okay?
Yeah, that is fine. Yes.
Okay. So the first one is just a convenience. That's what's called a magic command with a percentage sign at the start. It simply means that the output will be given as LaTeX typeset rather than just strings of characters. So we start off by noticing that the first thing that Sage can do is numbers of arbitrary precision. There's no limit on the size of numbers that Sage can handle. The only limit is the limit of your computer memory. So, and to enter, it's you can't see what I'm doing. It's Shift Enter, and in a few minutes you'll get a very long number. If you want to see it all, we can print it as a string. And there's the same number, but in ASCII rather than in typeset, LaTeX. And you also notice how quick it was. It did it almost instantaneously. If I just wrote factorial 1,000, it would give me but I'll do that. I'll put a little hash to indicate that is currently a and again, we've got a huge, long number, which goes miles across the screen and away into no man's land. But if I, instead of just writing it, I print it, then we see the whole thing, factorial 1,000, in all its glory. And again, notice how fast it was. We really didn't have to wait too long. It was almost instantaneous, milliseconds. And I think you'll agree that it's a beautiful large number, a very handsome number. Well, that's integers. The same thing for real numbers. Pi, of course, is known to Sage. It is most of the standard constants of mathematics. And n, the capital N, simply means a numerical approximation to as many digits as you like. 250. Take a few minutes, and I might actually print that so we can see it all at once. There we go. But if I wanted 2,500 digits, I could get that as well. I'm not quite sure how many digits it has in memory. I think it might have about 500,000 or thereabouts. If you wanted more, it would have to compute them, so it would be slow. But really, the time here is taken up with actually writing it to the screen. Anyway, that's sort of quite impressive, I think. And anything that involves real calculations, be it a function, can be done automatically. If Sage can do it, it can do it to arbitrary precision. I don't know if you know that e to the power of pi times the square root of 163 is very nearly an integer. There it is. It's a remarkable thing that it is so close to an integer. It's one of the so-called Heegner numbers, which comes out of the theory of modular forms and elliptic curves. I don't really understand the theory very much, but I do like the fact that e to the power of pi to the root 163 is so amazingly close to an integer. I mean, who knew? I think that's quite magical. Am I going too fast? Is this all right? I'll keep going, and you can just shout at me or ask me to slow down or shut up or whatever. Of course, it does primes. There's a nice little function called primes first n, which is exactly what it says. You do the first n primes in here, first 20 primes, or primes between two values, 100 and 200. It's very good with primes. It's also very good with factoring as well. I don't know why I did this. Do you know the book Gödel Escher Bach by Douglas Hofstadter? It was published in the early 1980s, I think, quite a long time ago. It was quite a famous book. And Hofstadter invented this sort of wild version of the Fibonacci series. You know, in the Fibonacci series, you just add the previous two values. Well, in this one, the previous two values tell you how far back to go to find numbers to add. So it's quite a chaotic sort of function, but we can write it almost exactly as this is just standard Python here, really, it's not Sage. But there's our first 100 values. Just to keep going with numbers, I learned quite recently the also remarkable fact that for these three numbers, pi squared, pi to the power of 2.5, and e cubed, so we call those values a, b, and c, then a squared plus b squared is remarkably close to c squared. And in fact, I think if we do this, let's have a look. So we define our values a, b, and c. A is pi squared, b is pi to the power of 2.5, c is e to the power of 3, and a squared plus b squared minus c squared is really remarkably close to an integer. And if we imagine those as being the sides of a triangle, then the side opposite c has an angle that's so very, very close to 90 degrees. So you've got, remarkably enough, these three numbers give you a triangle that's almost right angled. It's not obviously not exactly right angled, but you can see it's so very close to right angled. But the point of doing this is it's just demonstrating again some of the aspects of SAGE and handling, numbers and functions. And what I'm doing here clearly is applying the cosine rule to get the angle opposite C and multiplying it by 180 on pi to turn it into degrees rather than radians. And I'll talk about graphics a little bit later, but if we were to draw this, that's what it looks like. And in fact, that point there, it looks like it's on the y-axis. It looks like it's a right-angled triangle. It's not. That point is ever so far to the outside. It's actually a little bit to the left. And in fact, there's an error here because actually that should be a little bit over 90 rather than a little bit under 90. There's something wrong with the way it does the sign here. But anyway, the point is we have a triangle that's very nearly right angled and we can draw it. And just sort of continuing on with playing with numbers. So again, I don't know if you know about Python, but range, I'll quickly write this in. Range gives all the numbers, I should say range AB, where A and B are both integers, give all the integers from A to B minus 1. The point about Python is it starts all lists indexed at 0. There's sort of a long sort of discussion amongst computer scientists whether lists should be indexed at 1 or 0. And quite some years ago, Edgar Dijkstra, the famous Dutch computer scientist, claimed that 0 was the best place to start and wrote very persuasively about it. Well, Python starts at 0, but some languages don't. MATLAB, for example, starts at 1. And the reason for that is that, let's just quickly do this. So there you go. So if we add the reciprocals to the first 20,000 integers, we get a value slightly over 10. And as you know, because you've probably taught it to your students many times, this is a divergent series. So if you keep on adding the reciprocals, eventually you'll exceed any number you like, though it is, of course, quite slow growing. How are we going? Am I making any sense, or are you sitting there with spinning heads? And we were able to download those files I put in the chat. Well, I'll keep going. I hope you're listening, but it doesn't really matter if you're not, because, I mean, this is sort of self-explanatory. And once you download the files, upload them to CoCalc, you can sort of work it out from there. And I should say, before I forget, that send me your emails after this so that I can contact you. And the reason for that is that I actually haven't prepared a second workshop, deliberately haven't prepared it. So I thought I'd get a sense of what people were more interested in following up in detail or going further. So I thought I'd give a sort of a brief whistle-stop tour of some elementary aspects of SAGE today. And then tomorrow, we can either look at any of this in more detail and more depth, or we can explore something else. But that'll be up to you. You need to sort of tell me what you'd like to do. It goes without saying that SAGE knows all the functions you can think of. Obviously, all the trig functions, x, the e to the power of, log, all the hyperbolic trig functions, and many, many others, and many special functions that are used in mathematical physics and applications like Bessel functions and the like, all there. So let's have a quick look at those. So notice that unless you ask for it, Sage will endeavour to give you a sort of closed form solution. So if I ask the sine of pi on 3, it returns the closed form solution rather than a numerical approximation. If you wanted a numerical approximation, you'd have to ask for it with the capital N function, which, as you recall from before, gives you a numerical approximation. Of course, it does logs brilliantly. That's obviously log with just by itself is your natural log. But you can have a log to any other value by including a second parameter in the log function. So here we'll look at the log of 81 to the base of 3, which as you'd expect is 4, because 3 to the power of 4 is 81. Lambert's function is one you might not know about. It's quite a cute function. I sometimes use it with my students for doing numerical approximations with. It's inverse of x times e to the x. And so the value of Lambert W function at 5 is 1.3, and 1.3 times e to the power of is, of course, 5. I'm just showing you that to show that Sage knows quite a lot of other functions, sometimes quite obscure, sometimes fairly well known. And if you go to, I think it's Sage documentation, let's have a look at the reference manual very quickly here. Mathematics. It's a whole list of all the functions it has somewhere. This manual. Can't remember where it was. Anyway, I'll find it for you before tomorrow. There's a whole list of all the functions it has. Masses of them, all these different weird and wonderful functions. You know about the gamma function, of course, the function that interpolates the value of the factorial function. So it allows you, if you like, to take a factorial of negative and non-integer values. And, well, as you know, if n is an integer, gamma of n is the factorial of n minus 1. So the value of gamma of 6 is 5 factorial, and gamma of a half is, well, square root of pi. And you can prove that quite easily from the definition, which I'm not going to do now because it will require fiddly integration. The error function, which you'll know from your statistics and probability. A couple of examples of the use of the error function here. Now, if you look for example, the normal distribution on Sage, you won't find it. And the reason you won't find it is it's actually not necessary. Sage doesn't have to have it. It's already there as part of a Python library. Sage doesn't need to know itself about the normal distribution. That's held in the SciPy library of Python under the stat sub package. So you can use that sort of package to find out the value of the normal distribution at 2, which we found out before from using the error function. So whatever Sage doesn't have itself, you can pull it in from innumerable other packages that it has as part of its ecosystem. Because when Sage was developed about 12 or 14 years ago, I can't remember now, the idea was, as they used to say, not to reinvent the wheel, but to build the car. And what they meant was to take all the best open source mathematics packages currently in existence and bring them all together under one common interface. And then they would add extra functionality as was needed. And this has actually worked out very, very well. And it's not even obvious to you what's going on. If you put in a request, you put in a command, that command will probably be managed by one of the subsystems of Sage, which there are many, many. A lot of the calculus, for example, is handled by Maxima or SymPy, Python's own internal symbolic program. That's a little thinking about elliptic. Do you know about elliptic integrals? Elliptic integrals are used, for example, to determine the circumference of an ellipse, which there's no nice closed form formula, but you can, of course, write an integral representation of the circumference of an ellipse, and the integral that gives that is one of the elliptic integrals, so-called elliptic integral of the second kind. And there are two others. And I just made a few little comments here about using elliptic integrals to determine the circumference of an ellipse. And if I should put this through, let me have a quick look at what I've got here. I have an error. Oh, I shouldn't be getting an error. Real number has no attribute variables. What's going on here? Variables 3, 2. Oh, I know. One thing that is a slight gotcha in Sage is the fact that you can't, when you use a variable, you've got to declare it first. So this last line here is looking as an integral involving a variable x, the standard name of our variable for integrals and derivatives. But to use x, we have to declare it to be a variable. Having done that, then we can just use it. And the point about this is, it's maybe not very obvious from the way I've written it, but here is, we imagine an ellipse whose major and minor axes are of length 3 and 2. And in that case, the circumference of the ellipse as an elliptic integral is given by this formula here, 4 times a times the complete elliptic integral of 1 minus b squared on a squared, and you'll probably notice that is the square of the eccentricity of the ellipse. And here's exactly the same thing done as an integral, and here I'm using the parameterization of the ellipse, you know, x equals a times cos of t, y equals b times sine of t. I probably should use t here rather than x, but it doesn't matter. And you get the same result, as you would hope. It'd be a bit embarrassing if the elliptic integral gave you a different result. All right, so numbers and functions. By the way, what's the time in Prague at the moment? Is anyone in Prague at the moment? What's the time there? I'm in Melbourne, Australia, where it's just gone midnight. So the joys of international conferences, huh? We're all over the world. So, of course, being a computer algebra system, it's got to be able to do symbolic algebra, which, of course, it does extremely well. And very elementary expansion. Again, there's no limit on the size of the expansion. Now I could make it bigger, for example, let's say x plus 2 times y minus 3 times z plus 4 times w. I'll include z and w in there. And we get this rather splendid expansion. But again, it happened, as you saw, almost simultaneously. The lag, such as it was really writing the answer to the screen. And of course, you can factorize, as well as you can expand, of course, you can factorize. I've just put this one here. And there we go. So factorization will aim to factorize over the integers. But we can, with a little bit of work, factorize over extension fields. So if we append to the ring of integers the value square root of minus 3, which is what we're doing here. We're creating a quadratic field which is extending the integers by square root of minus 3. Then, having done that, we can factorize that even further. Now, I'm not going to go, I'm just going to sort of leave this here. I'm not going to explain it because it would take too long. But the point I would wish to make is that Sage can manage with, really the power of Sage comes with defining variables to be members of some particular ring or field, and then everything you do is related to that particular ring or field. And we'll look at another way of doing this in a few minutes. Of course, it does partial fractions. There's the partial fraction of x on x to the 4 minus 1, the sort of thing I'm sure you've given your long-suffering students over and over again. I mean, we all love our partial fractions, don't we? We do that in our calculus 1 or 2. But the other thing we can do, as I said before, Sage contains within it a vast number of other sort of subsystems. And one of those is maxima. And if you want to look it up, you look it up as, I think it's, let's have a look, very quickly to show you that. So it's GNU maxima. Maxima is a very, very venerable system. It goes back to, I think it was developed in the 1960s and early 70s. This current version, Maxima, is a fork of a version of the original Maxima, which was released as source code to, I think, the US Department of Energy a long, long time ago. Somewhere there should be a... Anyway, look, it's a good system in itself. It's very good for calculus. But because it's part of Sage, we can sort of use it just by saying, well, we're going to use Maxima now. I don't know what that's doing there. So here's two factorizations of x to the 6 minus 1. One is just the same factorization we had before. The other one, and Maxima does this, and this is really very neat, Maxima allows you to extend the field you're working in by a minimal polynomial which defines the extension. So before we defined the square root of minus 3, we added that to make an extension field. Here we're defining the minimal polynomial, which is clearly a squared plus 3. and it allows us to factorise x to the 6 minus 1 as all of this, understanding that a means the square root of minus 3. And it's maybe not immediately obvious, but this result here is the same as this result here, just written in a slightly different fashion. And you can also do it directly by just using maxima dot factor. So 2 ways of doing the same thing. What I thought when I prepared, I sort of pulled together a whole lot of ideas. It seemed to me to give a reasonable sense of sort of the breadth of SAGE at a fairly sort of elementary level. If I'm leaving people behind, and if you would wish, why isn't he talking about this? I would ask you to make a little mental note and just email me after this. If I've got my email, I'll put it in the just in case you've forgotten it, you should just email. I'll put it in my chat now. Oops. So I would very much welcome emails, especially so that I have some ideas of what I can do in the next workshop. Because as I said before, I deliberately haven't prepared anything for the second workshop. I thought I'd wait and see how you felt about the first one and where we might go with it. So the rising factorial, that's one of those sort of standard things. So what we have here is x times x plus 1, blah, 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 all the way up to x plus 7. And if we expand that, we get this sort of handsome expression here. The coefficients of this particular expansion are what are known as Stirling numbers of the first kind. They're sort of a cousin of the better known binomial coefficients. And in fact, if we, and SAGE knows all about Stirling numbers, but if we do this, you will see that the list of Stirling numbers in this list here are exactly the coefficients that we had from the expansion. Stirling numbers are great fun. There's a lot of good things. One tends not to study them if unless one's a combinatorial expert, but I don't know, I think they're great fun. It's one of those sort of things that I wish we knew more about. As well as factoring and expansion, SAGE can do simplification of all sorts. Here's a sort of a fraction of fractions, a so-called continued fraction. And if you sort of simplify that, you will get this as a single fraction. All right, how are we going? It is, got 15 minutes to go, probably a bit less. I think we're meant to finish a bit early. So again, we'll make x a variable. So calculus, we all want to know about calculus. Calculus is sort of our, as mathematicians and mathematics teachers, calculus is very much our bread and butter. Just off with a little sort of solution of a cubic polynomial. As you will know, quadratics can be solved with the quadratic formula. And as you probably also know, there's an equivalent, though much, much more complicated, formula for solving general cubic and quartic polynomials, but there isn't one for general fifth degree polynomials. But SAGE can solve any cubic or quartic polynomials and give you a solution in closed form. So back to calculus, derivatives to any level. So here I'm looking at e to the power of sine x. and differentiating it 4 times, and get this lovely expression here. So I'm sure will give you all, the warm and fuzzies. You look at something like that and you sort of feel good about the world. I'll give myself here. Oh, yes. This is the integral of the square root of 1 minus sin x squared on 4. It is, in fact, an elliptic integral, and that's exactly what Sage has given us. It's given us an elliptic integral as the answer, which is, in fact, quite correct. So sometimes, if it gives you a value, you might need to interpret it in view of the many, many functions which Sage knows about. Excuse me. Here's an integral of a rational function, 1 on x cubed minus 6x minus 6. We would expect to be able to do that using partial fractions, and indeed we can, and that's what you get. I think you'll agree it's a rather splendid sort of expression, don't you think? Who'd have thought? It's one of those things that bedevils first and second year students, or students starting their journey into mathematics and especially calculus, is how very, very complicated integrals can get. Quite two integrals that are seemingly very similar, aside from something very maybe minor looking at, will have a vastly different output. So I don't know about you, but I think that's a very fine result indeed. So integrals, do lots of integrals. Whether it's comparable to something like Mathematica, I've got no idea. It might not be, but then again, it's free, whereas Mathematica costs, a lot of money. It's pretty good. It'd be fairly hard pressed, I think, to find an integral which Sage was unable to do. And of course, you can always do numerical integrations. So there's obviously Taylor series. There's tan of x around 0 going up to degree 12. So you might think of this as a Maclaurin series since it's expanding around 0. Same thing for sec. And I added them both together. But, again, Taylor series of pretty much any function you like to throw at it, it can do. And for some reason, I don't know why I put this here. I've got a binomial coefficient. It does all the binomial numbers. I don't quite know why that's sitting there. Maybe it's left there from a previous or older version of this worksheet. Did you know have you ever come across alternating permutations before? So here are the alternating permutations of 4. They are the ones for which, starting at the very first number, you go up, so the second number is bigger, the third number is smaller, the fourth number is bigger. So an alternating permutation, you go up, bigger, smaller, etc., until you reach the end. And so for 4, there are 5 different alternating permutations. So the number of them is 5. It turns out, though, what's a particularly nice fact is known as Andre's theorem, and it's nice because it gives a little bit of structure to the series for tan and sec, which seem so completely lacking in structure, unlike the rather nicer series for sine and cos, that the series for sec x plus tan x is given by the number of alternating permutations divided by k factorial times x to the k. And if we do that, there's our number of alternating permutations And if I turn them into a series, what we have here is exactly what we had up here. So a nice little snippet of information. So you can get the structure of the series for tan and sec by using this rather delightful idea of alternating permutations and their numbers. Moving right along, you might know about the Bernoulli numbers. They're a very, very important and famous set of numbers. They come up all over the place. And they are defined as the generating function for them is x divided by e to the x minus 1. And it's not immediately obvious, but these numbers are the Bernoulli numbers divided by the appropriate factorial. So I multiply the coefficients by the factorials. Those are the first lot of the Bernoulli numbers. We're nearly at the end. We're only halfway through. We'll show you a few quick plots, and then we'll be able to call it quits, I think. Plotting is fine. All sorts of plots. You can do plots of a single function, sine of x between 0 and 4 pi. Sort of pretty much exactly what you'd expect, a fairly standard sort of syntax for a plot. You can plot two functions together by putting them together as a list inside square brackets. So cos x and sine of x together. I haven't done this, but you can also go legend, so you know which one is sine and which one is cos. I mean, we know, but if you're showing this to somebody else, you might want a legend. So the blue graph is this and the green graph is that. You can do parametric plots with the command parametric plot. You'd expect this one to give you a circle, as indeed it does. And the famous Lissajous figures, when you use sine times one thing and sine times something else. So this is very similar to the Australian Broadcasting Corporation symbol. You can change that to something else. Let's make that 5. And we get this beautiful thing. Now, it being now's the time I'm supposed to stop. Do you want me to go for another 7 minutes, or shall I stop and you can shout at me for a bit? What would you like me to do? No answers?
No. There are responses, but we are sorry for the delay, the technical difficulties.
Oh, that's all right. There's already I'm very impressed you
causing
managed to get it working at all.
some trouble, but like a minute ago, everyone left from here that was present. So it's up to you that are online. So.
Well, what I think I might it's now 12:24. Is there more? Is there something else starting at? Yeah, there's something else starting at in a few minutes. I think you should have a couple of seconds to get yourself a breath of fresh air. And but again, what I would strongly encourage, in fact, I request that you do it. If you want to come again tomorrow, and I'd love to see you, of course, we can continue this. We can go over more of this. Please email me and let me know what you'd like, and I will base tomorrow's workshop on what you'd like to see. I can go through more of this we've just done. I can do something new. I can take a single topic and go deeper, or I can take some more advanced mathematics. It's your call, and as long as I understand it, I'll have a go at it. Yes.
Hello. Hi.
Hello. How nice to see you.
Hi. Nice to see you. I'm at home now. Could you tell me any story about over there? You see, you want to solve a third-degree polynomial equation.
Yep.
Exactly, right?
Yep.
And you put that under the category of calculus. Was that right?
Well, yeah, it wasn't really. It should have been algebra.
Yeah,
I-
there
I-
should be algebra.
Could have been algebra. It was only there really by mistake, and because I was going to use it again. But if I go back to algebra, where were we? Let me just.
Yeah, right.
let's say,
You know, it depends on, you know, I'll be asking your age whether if you have ever been taught the method for solving that equation at school.
I was never taught it at school. No.
Yeah.
I was.
No, then you are younger than I am.
Well, in fact, I don't think at any time in my mathematical journey from school to university we ever discussed the actual cubic or quartic
Equation like that.
equations. Though it's I guess it's a little bit old-fashioned because I think now we're not so much concerned about what the solutions might be, but whether a solution exists, and if it does exist, what form it has. I certainly studied Galois theory, but
Right.
I thought I'd just very, very quickly show you if I do a times x cubed plus b
Oh,
times
boy.
x squared,
Oh.
b times x plus d.
Yeah.
You may have to declare ABCD, no?
Yeah, so there you go. So there's the three solutions.
Okay.
It's beauty, isn't it? And there's a similar one for the fourth degree, but I mean, it's the interesting thing is that it exists, but it's far, far too complicated to use. So yeah, so there's a whole lot of other things I'd love to have done. Roller coaster loops are terrific. I was going to show you some of those. The Joukowsky transform, which creates airfoil shapes, and a little bit of numerical mathematics and some linear algebra to finish. But if you can download the files I sent before, that'd be great. If you can't, just email me and I'll send them to you directly. I think we better stop because it's nearly what time is it? 2:30 for you, is it? Yeah, 2:30 for you in Prague. midnight for me in Melbourne.
Exactly. So it had to be challenge for you, but it was great. Thank you.
Well, look, I find talking keeps me awake.
Okay, so thank you to everyone. As I said, everyone that was present physically here, present in person. That's the formulation I was looking for. Already left, so I'm here alone. But I believe it was interesting for them. But they just went for another meeting. So
That's all right. There's a lot of things going on.
Probably join for the second part.
Excellent. Thank
Okay.
you all. It's been good talking to you all. And as I say, any questions, just email me and we'll see some of you, I hope, or all of you tomorrow evening.
Yeah,
tomorrow
yeah.
afternoon.
They might look at the recordings.
Yes, and the recordings as well. Absolutely.
Yeah, right. Yeah.
Thank you and
See
goodbye.
you all. See you all.
And good night.
Next tomorrow.
Thank you very much, Professor McEnroe.
Bye.
Yeah. Okay. Bye.